Welcome back. Let's review cash flow duration and immunization. All right, so in this video, we are going to be reviewing the fifth unit of financial mathematics, at least the way that I have decided to break up the topics. And the fifth unit is all about cash flow duration and immunization. In particular, we're going to be reviewing the topics that I cover in lessons 31 through 35 of my financial mathematics series. And so that includes the Macaulay and modified durations, the Macaulay and modified convexity, asset liability exact matching, Redington and full immunization, and price estimation using durations. Okay, so if you haven't watched my lesson videos on these topics or you're not familiar with these topics, I would encourage that you watch those videos first, or at least become familiar with these different concepts before you watch this video, because it is a review video. I'm going to assume that this is not the first time that you have seen these different concepts. Okay, now just like with my other unit review videos for financial mathematics, the first thing we're going to do is review all the different formulas you need to know for Unit 5, so all the different formulas from these different lessons, and then once we're done reviewing those formulas, we will start working through some review problems. Okay, and so let's not waste any more time, let's take a look at our first set of formulas. Okay, so first up we're going to be looking at formulas related to durations. Remember that there are two different types of durations. There is a Macaulay duration and a modified duration, and the two types of durations are related to each other. We'll talk about that in a second, but they also have their own separate ways of being calculated. And so let's start with the Macaulay duration. You can calculate the Macaulay duration for a set of cash flows by taking what I call a time-weighted present value of those cash flows and dividing it by the present value of those cash flows. Okay, now we do have this somewhat complicated mathematical notation here, but what it's saying is we're taking the sum of the present value of our cash flows. C sub t represents a cash flow at time t. We're multiplying it by a present value factor to the power of t, so it's bringing that cash flow back in time, the appropriate number of periods to have it valued at time 0, but then we're multiplying each of those cash flows by the time at which they are made, or the time at which they are received. Okay, and so you do that for every single cash flow and add them all together. I know it looks kind of complicated, but really all this is in the numerator here is the present value of your set of cash flows, but where each cash flow is multiplied by the time at which it would be received, or the time associated with that cash flow. Okay, and then of course in the denominator here, this is just the sum of the present value of your cash flows. So this is the total present value of all the cash flows in your set of cash flows. So that's how you calculate a Macaulay duration. Now, from this calculation, you could also find a modified duration, because a modified duration is actually equal to a Macaulay duration brought back one period. All right, you would multiply the Macaulay duration by a present value factor using the appropriate interest rate, and that would give you the modified duration. Now, if you were to take this equation and solve for the Macaulay duration instead, let's say you know what the modified duration is, you could calculate the Macaulay duration by taking the modified duration and accumulating it for one period using the appropriate interest rate. Okay, so really we have the same formula here, it's just that this one is solved for the mod D, but this one is solved for the mac D. Okay, and so this is the relationship I was referring to earlier between these two different types of durations. If you know one, you can find the other by using these formulas. All right, now there is another way to find a modified duration and a Macaulay duration, and that is to use present value functions or price functions. And that's what I have over here. You can find the modified duration for a set of cash flows by taking the negative derivative of the price function or the present value function for that set of cash flows and dividing it by the price or present value function. All right, and remember that a present value function is essentially the same as writing out how you would calculate the present value for a set of cash flows, but where you write out the calculation explicitly in terms of the interest rate. And so then depending on what you want that interest rate to be equal to, you could plug that in for I in the equation to evaluate it. Okay, so if you want to know the modified duration at a specific interest rate, that's the value of I that you would use in the derivative of the present value function and the present value function in this formula. And then because of the relationship between the modified duration and the Macaulay duration, the MACD is just the mod D accumulated for one period, you can take this formula and multiply it by 1 plus I, and that will represent the Macaulay duration for a set of cash flows using a price function or present value function and its derivative. Okay, so these two formulas are an alternative way to calculate a modified duration and a Macaulay duration. Now, I will say this, you will probably use this formula the most often along with this relationship formula or these two formulas. In most cases, it is going to be easier for you to calculate a Macaulay duration this way, or if you need a modified duration, you would first calculate the MACD and then convert it to a mod D. But if you are given a price function or present value function explicitly, then you should probably work with these formulas. Okay, so that's generally my advice is if you're given a price function, then obviously you want to use these formulas, but otherwise you want to do it this way. It's going to be easier than creating your own price function. Now, there are exceptions to this. Sometimes it can be very difficult to actually evaluate this part in the numerator, the time-weighted present value for your set of cash flows, especially if you're working with, say, a perpetuity where the payments go on forever. Sometimes that can cause some issues with this calculation, and so in a situation like that, where calculating the MACD this way is kind of difficult, then maybe you want to work with these formulas instead and create your own present value function, take its derivative, and go from there. Okay, so that's my advice on how to go about calculating durations with these formulas. But now let's move on to our next set of formulas. Next up, we have the formulas for calculating the duration of a portfolio of assets. This is something that you may encounter from time to time. You may be given a group of assets, maybe it's different types of bonds or different types of annuities, whatever it may be. You may have a portfolio of different assets, and you may need to find the Macaulay duration or modified duration of that portfolio. And the way you go about it is by taking the sum of the present value of each asset and multiply it by their respective Macaulay duration. So if you have 3 assets, you would take the price of asset 1, multiply it by the Macaulay duration of asset 1, then add that to the price or present value of asset 2, multiplied by the Macaulay duration of asset 2, and then you do the same thing for the third asset. You take its present value, multiply it by its Macaulay duration, add that to your previous 2 terms. That's what's in the numerator here. You're just taking the product of the present value and Macaulay duration for each asset and then summing them all together, and then you're dividing by the total present value of the portfolio, which I have down here is just the sum of all the present values of your assets. So the present value of asset 1 plus the present value of asset 2, and so on. Okay, it's the sum of all the present values. And so that's how you would calculate the Macaulay duration of an entire portfolio of assets. But if you want to know the modified duration of the portfolio, it's actually very similar. It's the same exact formula, except you replace the Macaulay duration with the modified duration. Okay, so you need to know the modified duration of each asset in order to do this calculation. Now, remember, the modified duration and Macaulay duration are related. And so just like I've mentioned before, you can take the Macaulay duration of a portfolio of assets and convert it to a modified duration of the same portfolio of assets by multiplying by a present value factor. And in the same way, you could take the modified duration for the portfolio and multiply it by an accumulation factor to get the Macaulay duration of the portfolio. Okay, so that relationship still reigns true. But that's it for how we calculate the duration of a portfolio of assets. Next up, I have 2 shortcut formulas for calculating the Macaulay duration of a bond. If you have a bond with annual coupons and an annual yield rate, you can use this formula to calculate the Macaulay duration of a bond instead of using the traditional formula for calculating the Macaulay duration. You could take 1 plus I divided by I minus 1 plus I plus N times the quantity R minus I, all divided by R times the quantity 1 plus I to the power of N minus 1 and then plus I. Okay, and of course N is the total number of coupons, I is the annual yield rate, and R is the annual coupon rate. Now, if you have semi-annual coupons and a semi-annual yield rate, which is most likely what you will have, most bonds have semi-annual coupons, then this is the formula that you would want to use. You have 1 plus that semi-annual yield rate divided by 2 times the yield rate minus 1 plus the yield rate plus N times the quantity R minus the yield rate, all divided by 2R times the quantity of 1 plus the yield rate to the power of N minus 1, and then plus 2 times the yield rate. Okay, and N is still the number of coupons, but now R and the yield rate are both semi-annual rates. Okay, so you could use this to calculate the Macaulay duration of a bond if it has both a semi-annual coupon and yield rate. Now, whether you actually want to use these formulas is up to you. You can still calculate the Macaulay duration using the formula we looked at earlier, the traditional formula. You just have to remember to account for all of the coupons as well as the redemption value that is returned at the end of maturity. And one more thing, of course, these two formulas only calculate a Macaulay duration. So if you want to get a modified duration for that bond, once again, you want to use that relationship that I've talked about a couple times now. You would want to multiply these formulas by present value factor V using the appropriate yield rate, and that will give you the modified duration of that bond instead of the Macaulay duration. Okay, and so that's it for these two formulas. Now let's talk about convexity. Remember that just like duration, there are two different types of convexity. We have the Macaulay convexity and the modified convexity. To calculate a Macaulay convexity, you want to use the same exact formula for the Macaulay duration, except the time-weighted present value in the numerator involves t squared instead of t. And here's what I mean by that. You take the present value of each cash flow and multiply it by the time associated with that cash flow, except now that time will be squared. Okay, so a cash flow at time 2, you would take the present value of that cash flow, but multiply it by 2 squared. A cash flow at time 3, you would take its present value and multiply it by 3 squared, and so on. Okay, so really all it is the present value of a set of cash flows, but where each cash flow is multiplied by the time associated with that cash flow, but that time is squared. All right, so you take that and then you divide it by the present value of your set of cash flows, just like you do with a Macaulay duration. Now, if you were able to calculate both a Macaulay duration and a Macaulay convexity, you can use those two values to calculate the modified convexity. The modified convexity would be equal to the sum of the MACD and the MACC, and then multiplying that sum by a present value factor squared. Okay, so this is a nice relationship between the two Macaulay calculations and the modified convexity. All right, now if you want to work with a price function or a present value function instead, you can still do that. You can calculate the modified convexity by taking the second derivative of the price function or present value function and dividing by that price or present value function. Now, if you want to calculate the Macaulay convexity using a price function, what you would have to do is use this formula. You would want to find the modified convexity as well as the Macaulay duration, and then you would be able to solve for the Macaulay convexity in this equation. Okay, so that's how you'd go about that if you needed to calculate the Macaulay convexity that way. All right, but those are all the formulas you need to know for convexity. Now let's talk about our two approximation methods for estimating or approximating the price of a set of cash flows given a change in interest rates. To start, we have the first order modified approximation, which uses a modified duration to approximate a price. We have that the new price of a set of cash flows, P of I sub n, where I sub n is the new interest rate, that new price is approximately equal to the original price, or the price at the original interest rate, that I call I naught. And by the way, if you don't know what naught is, it's just another way of saying zero, but it's easier to say faster. So that's all that is. But then you take that price and multiply it by 1 minus the change in the interest rates. So you have the new interest rate I sub n minus the original interest rate I naught, and then you multiply by the modified duration that is calculated using the original interest rate. Okay, now a couple things to note here. You could represent the difference in those interest rates, the new one minus the original one. You could represent that with delta I, that represents the change in the interest rates. Typically, we associate delta with the change in a variable. If you've taken calculus before, this should look familiar. You've probably seen delta x at some point or delta y. It's the same thing here. Just like delta x is a change in x and delta y is a change in y, delta I is a change in I, the interest rate. Okay, and in a similar manner, delta p represents the change in prices. Delta p would be equal to the new price minus the original price. And of course, this would be an approximate change in the prices because this right here is an approximation. All right, that is an approximated new price at that new interest rate. And then on that same note, regarding the change in prices, we can actually manipulate this formula a little bit to get two more formulas that are pretty nifty, that are helpful in certain situations or in certain FM problems. You could also approximate the change in the price delta P by taking the negative original price times the change in interest rates times the modified duration at the original interest rate, and then you can approximate the percent change in price, which would be delta P divided by the original price. You can approximate that by taking the negative change in the interest rates and multiplying that by the modified duration at that original interest rate. That calculation will give you the percent change in price as a decimal, so then if you do want the actual percentage, you would need to multiply by 100. Okay, so these are all formulas surrounding the first order modified approximation, but there is another approximation method that you should know, and that is the first order Macaulay approximation. And this approximation method, as you may be able to guess, uses a Macaulay duration to approximate a new price for a set of cash flows given a change in the interest rates. And the formula looks like this. The new price at that new interest rate is approximately equal to the original price at the original interest rate times the quantity of 1 plus the original interest rate divided by 1 plus the new interest rate to the power of the Macaulay duration that is calculated using the original interest rate. Okay, and very similar to the first order modified approximation, you could find the change in the interest rates by taking the new rate minus the original rate, and you could approximate the change in prices by taking the new price minus the original price, but you can't calculate it any other way with any other special formulas like you can with the first order modified approximation, because in that formula, you could actually manipulate it and solve for delta P as well as the percent change in price. You could still do those calculations for a Macaulay approximation, but you can't do them in any special way. To approximate the change in price, you must take the new price minus the original, and then if you want the percent change, you would then take that delta P, or that change in price, and divide it by the original price. Okay? And then one more note, these are two different approximation methods. The first order modified and Macaulay approximations are different methods. They will not give you the same answer, so do pay attention to problems when they tell you what type of approximation to use. Okay, if you're told to use the first order Macaulay approximation, you have to use this formula. You can't use the modified approximation method, and the same would be true in reverse. If you're told to use the modified approximation, you have to use that formula, not this one. Okay, now moving on. On more of a simpler note, let's take a quick look at asset liability exact matching. When you use this method of managing assets and liabilities, essentially what you are doing is matching every single liability that you need to pay off in the future with an asset of the same amount. Okay, so at every time 1, time 2, and however many times there are, however many assets or liabilities you have, if you are exactly matching them, the asset at time 1 should be equal to the liability at time 1, the asset at time 2 should be equal to the liability at time 2, and so on. These two cash flows are equal, and these two cash flows are equal, and that would remain true for all values of time where you have an asset and liability. And so because of that, hopefully it makes sense that the present value of the assets should be equal to the present value of the liabilities, since the value of them is the same at each moment in time. If you take their present values or calculate their cost, it should be the same. All right, so that would also be true when you are exactly matching assets and liabilities. But now remember, exact matching is not the only method of managing assets and liabilities. We also have immunization. And there are two different types of immunization. There is Redington immunization and full immunization. Redington immunization is the weaker type. It protects assets and liabilities from adverse effects in small changes of interest rates, while full immunization protects assets and liabilities from adverse effects in all changes of the interest rate. Okay, so full immunization is a stronger type of immunization when compared to Redington. Now, for both types of immunization, there are 3 conditions that must be met in order for a set of assets and liabilities to be protected or to be immunized at a specific interest rate that we call I-naught. The first 2 conditions are actually the same for both Redington and full. The first condition is that the present value or the price of the assets at that interest rate is equal to the price or present value of the liabilities at that interest rate. All right, so that's the same condition for both Redington and full immunization. That's the first condition. Then the second condition is that the duration of the assets must be equal to the duration of the liabilities. And you could use the Macaulay duration for that or the modified duration, whichever is more convenient. All right, so once again, that second condition is the same for both Redington and full immunization. Where the paths diverge is with the third condition. For Redington immunization, the convexity of the assets must be greater than the convexity of the liabilities. And you could use the Macaulay convexity or the modified convexity to check that. It doesn't matter. Whichever type of convexity is easier for you to work with, which in most cases is going to be the Macaulay convexity, but whichever one is easier is the one that you should work with when you are checking this condition, or if you're working with that condition in a problem. All right, but that's the third condition for Redington immunization. For full immunization, on the other hand, the third condition is a little bit easier to work with, and all it is that each liability is preceded and followed by an asset. And the way I like to think about this is like a sandwich. If you have a liability in your timeline for assets and liabilities, every single liability should be in between two assets. You should have an asset liability sandwich where the assets are the buns and the liability is the meat. Okay? One liability should be in between two assets for your entire set of assets and liabilities in order for full immunization to be possible. The other two conditions also need to be met, but this third one definitely needs to be met if you're going to have full immunization at a specific interest rate, I0. Okay, so unlike some of our other formula sets, these really aren't formulas per se. They're more like conditions that you can work with to create equations that will allow you to solve problems involving immunization. All right, so you're going to want to commit these conditions to memory if at all possible. But with that, those are all the formulas that I wanted to review for Unit 5. And so we're ready to move on to our review problems. But I did just want to say this real quick. We just looked at a lot of different formulas. We are not going to use all of them in the review problems in this video, but that does not mean that you may not need to use some of them in different problems that you may encounter when working with topics from this unit. Okay, so we're probably not going to use all the formulas that we looked at here, but don't think that that means that you don't need to know them for other problems, because you probably will at some point. All right, but enough about that. Let's take a look at our first review problem. Okay, so here's our first review problem. Before I read through it, I do want to remind you that this is a review video, so if you want to challenge yourself, if you want to try to see how well you know these different concepts, what I'd recommend that you do is pause this video every time we start a new problem and try the problem out for yourself. And then when you finish, or if you get stuck, feel free to play the video again and compare your work to my work. Okay? However you want to use this video is up to you, but I would recommend trying some of these problems out for yourself before watching me work through them. But now, with that being said, let's get started on this first example. We have an investment today returns $500 in 1 year, $600 in 3 years, and $800 in 7 years. Assuming an annual effective interest rate of 6%, for this set of cash flows, find the following. And we want to find the Macaulay duration, the modified duration, the Macaulay convexity, and the modified convexity. All right, and so let's do one at a time. Let's go in order here. I'll start with the Macaulay duration. That's what we'll calculate first. But before we do any of that, before we do any calculations, what I recommend that you do in a problem like this is draw a timeline organizing the cash flows that we've been given. And so that's what I'm going to do here. This will be time equals 0. But then we have $500 in 1 year. So this will be time equals 1. I'll put $500 right there. And then we have $600 in 3 years. So this is time equals 2, and this will be time equals 3. And so I'll put $600 at time 3. And then we have $800 in 7 years. So this will be time 4, 5, 6, and 7. All right, so this is time equals 4, time equals 5, time equals 6, and time equals 7. And at time 7, we have $800. Okay. And then one more thing I want to write down here. We are told that we have an annual effective interest rate of 6%. So I'll write that down here. Our interest rate I is equal to 0.06 as a decimal. All right, that is 6%. So now let's calculate the Macaulay duration for this set of cash flows. We'll have the Macaulay duration is equal to a time-weighted present value in the numerator. So we're going to take the present value of each of these cash flows. In other words, we're going to value them at time 0, but then we're also going to multiply each of them by the time that they are associated with, all right, or the time at which those cash flows would be received. So for the first one, we have $500 that needs to be brought back 1 year, and it's associated with time 1. So we're going to have 1 times 500 times a present value factor to the first power. All right, then we will add that to our next cash flow, which is $600 at time 3. We need to bring it back 3 years, and we want to multiply it by 3. So we're going to have 3 times 600 times v cubed. Okay, and then finally, our last cash flow is $800 at time 7. So we need to bring it back 7 years and multiply 800 by 7, the time associated with that cash flow. All right, so we have 7 times 800 times v to the power of 7. All right, so that's the numerator of our Macaulay duration calculation. Now in the denominator, we're just going to have the present value of these cash flows. So it's exactly what we have up here, except we won't be multiplying each cash flow by the time at which they are made. All right, so we're just going to have 500v plus 600 v cubed, and then plus 800 times v to the power of 7. All right, and that's all there is to the setup for the Macaulay duration. Now all you have to do is put all of this into a calculator. Remember that the interest rate here is 0.06 or 6%, so you want to use that in each of those present value factors. And if you do that, you should find that the Macaulay duration is about 3.7859 and some more decimals, but I'm going to round it off there. That is the Macaulay duration for this set of cash flows. All right, so that takes care of part A. Now let's move on to part B. We want to find the modified duration, and that should be pretty simple, right? Remember that the modified duration and the Macaulay duration are related. Specifically, they're related by a factor of a present value factor, right? The modified duration is equal to the Macaulay duration multiplied by a present value factor. In this case, we would be using the interest rate of 0.06. And so to calculate our modified duration, we'll take that Macaulay duration that we just found, which is 3.7859 and some more decimals, and we'll multiply it by 1 divided by 1.06, right? That is this present value factor to the first power. It's 1 divided by 1 plus the interest rate, which is 0.06. And so if you multiply the Macaulay duration that we calculated by this present value factor, you will get a modified duration of 3.5716 and some more decimals. That is the modified duration for this set of cash flows. So that takes care of part B. Now let's move on to part C. Let's calculate the Macaulay convexity. And remember that the Macaulay convexity is calculated very similarly to the Macaulay duration. The only difference is that these times that we're multiplying by the present value of each cash flow, those times will be squared. So here's what the Macaulay convexity calculation will look like. We'll have that the Macaulay convexity is equal to the following calculation. We'll have 1 squared times 500v to the first power plus 3 squared times 600v cubed, and then we want to add that to our last cash flow, but we're going to have 7 squared times 800v to the power of 7. All right, it's the same thing we have up here. We have the present value of each of these cash flows, but we're multiplying them by the time at which they will be received squared. We have 1 squared, 3 squared, and 7 squared. And then in the denominator, we just have the present value again. It's the same thing that we did before for the denominator of the Macaulay duration calculation. So we have 500v plus 600v cubed plus 800v to the power of 7. And so once again, if you use a 6% interest rate in each of those present value factors, and you put all of this into your calculator, you should find that the Macaulay convexity is equal to about 20.6140 and some more decimals. That is the Macaulay convexity for this set of cash flows. That takes care of part C, so we'll check that off. Now finally, we want to calculate the modified convexity, and we can calculate that by making use of values that we have already calculated, right? Remember this formula, the modified convexity for a set of cash flows is equal to the sum of the Macaulay duration and the Macaulay convexity, so MACD plus MACC, multiplied by present value factor squared, all right? And of course, we would be using that interest rate of 0.06 or 6%. And so we can calculate the modified convexity pretty easily because we have both the Macaulay duration right here and the Macaulay convexity right here. We already calculated those two values, so this is going to be pretty simple for us to do. This will be equal to 3.7859 and some more decimals plus 20.6140 and some more decimals multiplied by a present value factor squared, which would just be 1 divided by 1 plus the interest rate squared. So here's what I'm going to do here. I'm just going to divide those two values being added together by 1.06 squared. All right, so if you add the Macaulay duration to the Macaulay convexity and divide by 1.06 squared, you should find that the modified convexity is equal to about 21.7158 and some more decimals. That is the modified convexity for this set of cash flows. And so that takes care of part D, and that also takes care of this review problem. We have now calculated all four of the things that we wanted to find for the set of cash flows that we were given, and so we're done. Let's take a look at our next review problem. All right, so for our second review problem, we have an investor will receive payments of $125 in 2 years, $250 in 4 years, and $400 in 8 years. For this set of cash flows, find the following. And we have a lot of things we want to find, 7 different things in particular. We want to find P of I, the present value function or price function. We want to find the derivative of that function, the second derivative of that function, and then the modified duration using a 0.03 interest rate or 3% interest rate, the modified convexity using a 3% interest rate, a Macaulay duration using a 3% interest rate, and a Macaulay convexity using a 3% interest rate. Okay, so now if you want to try this problem out for yourself first, now would be the time to pause the video, and then when you're ready to compare your work to my work, you can play the video again, because now I'm going to start working through it. And the first thing I want to point out here is because the first 3 things that we are asked to find here are all related to the present value function, right? We have the present value function itself along with its first and second derivatives. Since we are going to be finding those functions or setting them up, it probably makes the most sense to then use them to calculate these different durations and convexities. Okay, so we will be making use of the alternative way to calculate some of these values. You just saw one way to calculate them in the previous example, but now in this example, we're going to do it in a slightly different way. Okay, but before we do anything, once again, I think we should set up a timeline to organize the payments or cash flows that we've been given in this problem. So I'll draw my timeline like this. We'll have time equals 0 right there. And then we have payments of $125 in 2 years. So this will be time 1, and then time equals 2. We have $125, and then $250 in 4 years. So this will be time equals 3, and then time equals 4. We have a payment of $250, and then $400 in 8 years. All right, so this is time 5, 6, 7, and 8. This will be time equals 8, where we have a payment of $400. All right, and so for these 3 cash flows, we want to set up a present value function, P of I. And all that is a function that represents how you would calculate the present value of these cash flows given an interest rate I. Okay, so this will be a function in terms of the interest rate I. So let's set it up. We'll have P of I is equal to our first cash flow valued at time 0. We need to bring it back 1, 2 periods. So usually we would write that like this. We would have 125 times v squared. But for a present value function or a price function, what you want to do is write out present value factors explicitly in terms of the interest rate. All right, so remember that a present value factor to the power of n is equal to 1 divided by 1 plus the interest rate to the power of n. But another way that you could write that would be 1 plus I to the power of a negative n, right? Remember from algebra that you can take a quantity in a denominator and move it to the numerator by making its exponent negative. All right, so what we're going to do instead of writing v squared is write this. We'll have 1 plus I to the power of negative 2. Okay, so that's how we'll represent the present value of that first payment. But now let's move on to the next payment. We have $250 at time 4. So we'll have plus 250, but we need to bring it back 4 periods. So we'll multiply by 1 plus I to the power of negative 4. Okay, that's just a present value factor to the 4th power. And then finally, let's add that to our last cash flow valued at time 0. It's currently at time 8, so we need to bring that $400 back 8 periods. So we have plus 400 times 1 plus I to the power of negative 8. And that right there is our present value function P of I. We have now completed part A of this problem. This represents how you would calculate the present value of this set of cash flows given a particular interest rate I. Okay, so now let's move on to part B. We want to take the first derivative of this present value function. And so we'll need to take the derivative of each of these terms individually and add them together for our first derivative. And so let's do that. We're going to have P prime of I is equal to the derivative of our first term. And so remember, we do have composite functions here. We have a function within another function. We have 1 plus I within a function of this quantity to the power of negative 2. So we would need to use the chain rule for derivatives here, which means we would take the derivative of the outside function and then multiply by the derivative of the inside function. But every time you do that, the derivative of the inside function is just going to be 1, because you're taking the derivative of 1, which is 0, the derivative of all constants is 0, and then you're adding that to the derivative of I to the first power, and the derivative of that will just be 1, because when you take the derivative of a variable to the first power, it's just going to be its coefficient, or the number in front of it, which in this case would be 1, right? This is just 1I, it's not 2I or 3I or anything like that, it's just I, so its derivative is 1, which means that when you would use the chain rule here, the derivative of the inside function is just 1, and so you can kind of ignore the chain rule, you can forget it exists. At least for taking the derivative of present value functions, all you have to do is use the power rule for derivatives on each of these quantities. You can multiply the exponents down and then subtract 1 from those exponents. Okay, so first up we have negative 2 times 125, so we'll have negative 250 times 1 plus I to the power of negative 3. All right, so we multiplied the exponent down. 125 times negative 2 is negative 250, and then we subtracted 1 from the exponent, so negative 2 becomes negative 3. Now next up we have this term. We'll multiply negative 4 down and subtract 1 from that exponent, and negative 4 times 250 is negative 1000. So we'll have minus 1000 times 1 plus I to the power of negative 5, right? Negative 4 minus 1 is negative 5. And then finally, we have this term. We need to multiply negative 8 down and then subtract 1 from that exponent. And negative 8 times 400 is negative 3200 or 3200. So we'll have minus 3200 times 1 plus I to the power of negative 9. All right, negative 8 minus 1 is negative 9. And that right there is the first derivative, P prime of I, of our present value function. That takes care of part B. Okay, so now we're ready to move on to part C, which is to find the second derivative of the present value function. And to find that, what we need to do is take the derivative of the first derivative. Okay, so we took the derivative of the original price function to get the first derivative, but to get the second derivative, we have to take the derivative of the first derivative. So let's do that. It's going to be a very similar process to what we did to find the first derivative. We're going to be multiplying each exponent down for those present value factors, and then we'll be subtracting 1 from those exponents as well. So for our second derivative, P double prime of I, here's what we will have. We'll have negative 3 times negative 250. That will be positive 750. So we have 750 times 1 plus I to the power of negative 4, right? Negative 3 minus 1 is negative 4. And then we'll have plus this term. Negative 5 times negative 1000 is positive 5000. So we have plus 5000. And then we need to subtract 1 from that exponent. So negative 5 will become negative 6. So we have 1 plus I to the power of negative 6. And then finally, for our last term here, we have negative 9 multiplied by negative 3200, which is positive 28,800. So let me write that out. We have plus 28,800 times 1 plus I to the power of negative 10, right? Negative 9 minus 1 is negative 10. And that's it. That is the second derivative of our price function, P double prime of I. And so that takes care of part C. We have now found the original present value function, and its first and second derivatives. And so now we're ready to move on to part D, which is to calculate the modified duration using a 3% interest rate. Okay, and we're going to calculate that with the help of these different functions that we just found, right? Remember that another way to calculate a modified duration is like this. The modified duration, in this case at 0.03, is equal to the negative first derivative of the present value function, which will be evaluated at 0.03, divided by the original present value function at that interest rate. Okay, this is how we can calculate this modified duration. And so what we want to do is plug 0.03 in for our derivative here, and then plug in 0.03 for I in our original present value function as well. If you do that, if you plug 0.03 in for the first derivative here, you should get about negative 3,543, and that does have some decimal values, but I'm just going to round it off there. And that will be divided by plugging 0.03 into our present value function. And if you do that, you should get about 655.71 and some more decimals. And so then these two negatives will cancel out, and you'll have this value divided by 655.71. And if you do that, you should get that the modified duration using a 3% interest rate is about 5.4047 and some more decimals. Okay, that is the modified duration for this set of cash flows at a 3% interest rate. That takes care of part D, so we'll check that off. Now we want to calculate the modified convexity using a 3% interest rate. And so remember that the formula for a modified convexity is very similar to the formula for a modified duration, except instead of using the negative first derivative in the numerator, we'll use the positive second derivative. All right, here's what I'm talking about. The modified convexity will be equal to the second derivative evaluated at 3% or 0.03 divided by the original present value function evaluated at 0.03. Okay, and so if you do that, if you plug 0.03 into this second derivative, you should get about 26,283.69 and some more decimals, and that will be divided by the original price function or present value function evaluated at 0.03, so this one right here. It'll be the same thing that we got over here for the denominator of the modified duration calculation, so I'll just write that in again. We have $655.71 and some more decimals. And if you do this in your calculator, you divide the second derivative evaluated at 0.03 by the original function evaluated at 0.03. You should get that the modified convexity is equal to about 40.0843 and some more decimals. That is the modified convexity for this set of cash flows that we were given at a 3% interest rate. And I did forget to write that notationally. Let me do that here. This should be the modified convexity using a 0.03 interest rate, or 3%. All right, and so that takes care of part E. We can check that off. Now we have two more values we want to find. We want to find the Macaulay duration at that interest rate of 0.03 and a Macaulay convexity at that interest rate of 0.03. But these we're going to find a little bit differently. What we're going to do is make use of the relationships between these two values and the other values we have already calculated. And for starters, let's look at the Macaulay duration. Remember that the Macaulay duration is closely related to the modified duration. It's just off by one period. In this case, we want to convert the modified duration to a Macaulay duration. And so that'll look like this. Remember that the Macaulay duration, in this case at a 3% interest rate, will be equal to the modified duration at that same interest rate, but brought forward one period. We'll be multiplying by 1.03, 1 plus that interest rate. Okay, the Macaulay duration is the modified duration brought forward one period, and the modified duration is the Macaulay duration brought back one period. All right, so we're doing the opposite conversion of what we did in example 1. Remember that we found a modified duration from a Macaulay duration. In this case, we're finding a Macaulay duration from a modified duration. So the conversion is the opposite of what we did last time. We're not using a present value factor, we're using an accumulation factor. Okay, and so let's do this calculation. Here's what it'll look like. If you take that modified duration of 5.4047 and multiply it by 1.03, you will get a Macaulay duration at 3% of 5.5669 and some more decimals. Okay, that is the Macaulay duration at a 3% interest rate for this set of cash flows. So we can check that off. That's part F. Now we have one more value to find, and that is the Macaulay convexity at a 3% interest rate. And to find that, we will also need to make use of a formula that expresses the relationship between these different durations and convexities. All right, in particular, this is what I'm talking about. Remember that a modified convexity is equal to a Macaulay duration plus a Macaulay convexity multiplied by present value factor squared, which would be the same as dividing by 1 plus I squared. Okay, so this is one way that you can calculate a modified convexity, but that's not what we want to find here. We already found the modified convexity. What we want to find is the Macaulay convexity, which is this value right here. So what we want to do is solve for that in this equation and then use the other values that we already know, meaning the interest rate, the Macaulay duration, and the modified convexity, and we will be able to find our Macaulay convexity. Okay, and so you can see from this equation that the way we would do that is by first multiplying both sides by this accumulation factor. So we would have the modified convexity multiplied by 1 plus I squared, and then we would want to subtract the Macaulay duration from both sides of the equation. All right, so here's what we would get. You would find that the Macaulay convexity at a 0.03 interest rate is equal to the modified convexity at a 0.03 interest rate accumulated for 2 periods. So we have 1.03 squared, right? Our interest rate is 3%. That's what we want to use. And then we'll be subtracting the Macaulay duration. All right, so we have minus the MACD at 0.03. All right, this is what you would get if you solved for the Macaulay convexity in this equation. So if you take the modified convexity of about 40.0843, multiply it by 1.03 squared, and subtract the Macaulay duration, which is about 5.5669, you should get that the Macaulay convexity is equal to about 36.9586 and some more decimals. Okay, sorry that I had to write that so small. I tried to squeeze it in here as best as I can. In fact, let me try to make that look a little bit better. All right, there we go. I tried to make it a little bit easier to see, not by much, but there it is. That's the Macaulay convexity at a 3% interest rate for this set of cash flows that we were given. And so that's it for part G, the final part of this second review problem. Okay, so for our third review problem, we have Flynn must pay liabilities of $1,000 due in 6 months from today and another $1,000 due in 1 year from today. To exactly match these liabilities, Flynn has 2 available investments. They are bonds A and B. Bond A is a 6-month bond with a face amount of $1,000, a 12% coupon rate, and a 10% yield rate. Bond B is a 1-year bond with a face amount of $1,000, a 9% coupon rate, and an 11% yield rate. Given that all coupon rates and yield rates are annual nominal rates convertible semi-annually, how many of each type of bond does Flynn need to purchase? Okay, so a change of pace here. So far we've really only worked with durations and convexity, but now in this problem we are dealing with a different concept from Unit 5. And so if you want to take a moment to pause the video and try this problem out for yourself, now's the time to do that, because now I'm going to start working through the problem. And so once you're ready to compare your own work to my work, feel free to play the video again. In this problem, we are dealing with the idea of asset liability exact matching. And the way that I know that's the case is because the problem tells us that to exactly match these liabilities, Flynn has 2 available investments. Okay, so we're told what his liabilities are, and now we're told that these are the assets he has to exactly match those liabilities. All right, and in problems like this, dealing with exact matching, I think it's always a good idea to draw a timeline. That way you can see exactly where your different assets and liabilities are and how they are going to be exactly matched. All right, so here's my timeline. This right here will be time equals 0, and then I'm going to wait to label the other times yet because we need to see what we're working with before we can determine that. And it looks like Flynn must pay liabilities of $1,000 due in 6 months from today, and then another 1,000 due 1 year from today. So it almost looks like we're working with semi-annual periods, and that is what we're working with. That's pretty much confirmed then by the fact that our bonds are working with coupon rates and yield rates that are convertible semi-annually, right? They're nominal rates convertible semi-annually. So we're going to be working with semi-annual periods here. So this right here will be time equals 1. That'll represent a period of 6 months. And then at time equals 2, that will be another period of 6 months. So this whole thing is just 1 year, which makes sense. That's as far as we need to go out for this problem, because he only has liabilities due in 6 months and 1 year from today. So that's good. Just remember that this is 1 year and this is 6 months. Okay? Just to kind of keep things straight. Now, let's put in the assets and liabilities. I always like to put liabilities below the timeline and assets above the timeline. That's just my preferred way of organizing the information. You can do it differently if you'd like, but this is the way I do it. We have 2 liabilities, 1,000 due in 6 months and 1,000 1 year from today. So we have 1,000 right here and 1,000 right there. Okay, so those are the liabilities. Now the tough part, let's talk about the assets, or the investments that Flynn has available. Bond A is a 6-month bond, okay? So that is probably going to be matched to the liability due in 6 months, since those time periods match up. Just like with Bond B, we have a 1-year bond. That's going to match up nicely with that other liability, but you have to remember to take the coupons into account, which we will talk about in a second. Let's go back to Bond A here. It's a 6-month bond with a face amount of $1,000, and it has a 12% coupon rate and 10% yield rate. Now remember, we are told that the coupon rates and yield rates are annual nominal rates convertible semi-annually, so we need to convert those rates into what they would actually be for our calculations. We probably won't actually make use of the yield rate in this problem, but the coupon rate is going to be important, so I'm just going to convert both of them anyway. The 12% coupon rate means that R will be equal to 0.12 divided by 2, which is 0.06. So we have a 6% coupon rate for Bond A, and then for the yield rate, it's 10% as a nominal rate convertible semi-annually, so the real yield rate J will be equal to 0.10 divided by 2, which is 0.05. And I'll do the same thing for Bond B as well. We have a 9% coupon rate and an 11% yield rate. So for Bond B, R is equal to 0.09 divided by 2, which is 0.045. And then the yield rate for Bond B, J will be equal to 0.11 divided by 2, which is equal to 0.055. All right, now I'm just going to give you a little spoiler here. We're not actually going to need to use these yield rates. We're really only interested in these coupon rates, because what we need to figure out is how much money would be coming in from each of these bonds at each moment in time for the assets in this timeline. Okay, let's start with a 6-month bond. Since the coupons are being paid semi-annually, that means that for Bond A, the first coupon will be the last. You're only going to get 1 coupon payment, and that will be at T equals 1 at 6 months in the future. So at time 1, the bond is over, and you're going to get 1 coupon and the return of the redemption value. So that's going to be a total of $1,000 plus whatever that 1 coupon payment would be. So to get the coupon payment, remember it would be F times R, and F times R in this case would be 1,000 times 0.06. So the coupon for Bond A would be $60. That's 6% of 1,000. So at time 1 for Bond A, you're going to get a coupon payment of $60 and the return of the redemption value, which we are allowed to assume is the same as the face amount in this case. So it would be a total amount of $1,060 received at time 1. Okay, so for Bond A, we have $1,060. Now, remember here, we are trying to figure out how many of each type of bond Flynn needs to buy to exactly match his assets and liabilities. So we're not just going to write 1,060 here, we're going to multiply it by a variable that represents the number of those bonds that Flynn would buy. Okay, each Bond A is going to give him $1,060 at time 1, and so we represent that by multiplying that amount by X, which is the number of those bonds. So if he bought 2 Bond A's, he would have 2 times $1,060 at time 1. Okay, X is going to represent the number of Bond A's. So number of Bond A is going to be X. Now, in the same way, I'm going to give Bond B a variable as well. I'll say that the number of bond B is going to be Y. All right, so bond B, the number of those that Flynn needs to buy will be represented by Y. And what would those payments look like for bond B? Well, it's a 1-year bond with semi-annual coupons, right? Since the coupon rate is convertible semi-annually, the coupons will be paid semi-annually. So you're going to get a coupon payment from bond B at time 1 and time 2, right? 6 months in the future and then another 6 months in the future. And what will that coupon amount be? Well, we need to take the face amount of 1,000 and multiply it by the coupon rate. So for bond B, we'll have F times R, which will be equal to 1,000 times 0.045, and that will be equal to 45, all right? 4.5% of 1,000 is $45. So that would be the coupon amount at each moment in time. And at time 1, that is all you're going to get from bond B, right? That's all Flynn is going to receive. So he's going to have 45 times Y at time 1, right? A $45 coupon for every single one of those bond Bs that he buys, all right? If he buys 2 of them, he's going to get 2 of those coupon payments of $45 at time 1. That's how we sort of represent that. We have 45 times Y. Okay, but then at time 2 for bond B, we'll also get another payment of $45 or another coupon payment of $45, but we'll also get the return of the redemption value of $1,000. We are allowed to assume that that is the same as the face amount in this case because we're not told otherwise. All right, so in total at time 2 or 1 year in the future, bond B will pay $1,045 for every single bond B. So we'll multiply that by Y. Okay, and that's it. That is all of the payments or the assets that Flynn is going to receive that he can use to exactly match his liabilities. Okay, and so what we want to do in this problem is determine how many of each of these bonds he needs to buy. We want to solve for X and Y. And to do that, we need to set up some equations, which are actually not too hard to set up. Remember that for asset liability exact matching, the assets and liabilities should be equal at each moment in time. So what that means for us is that at time 2, 1,045Y should be equal to 1,000, right? So that's our first equation. We'll have 1,045 times Y is equal to 1,000. We're going to be able to solve for Y pretty easily there, but before we do that, let's set up our other equation for time 1. This asset plus this asset should be equal to this liability. So we'll have 45Y plus 1,060 times X is equal to 1,000. All right, and so now our goal here is just to solve for X and Y, and we can start by solving for Y. That'll be really easy. We just need to divide both sides of the equation by 1,045. So if we do that here, we'll find that Y is equal to 1,000 divided by 1,045. And if you plug that into your calculator, you'll get that Y is equal to 0.95694 and some more decimals. That right there is the number of bond B that Flynn would need to buy to exactly match his liabilities. So that's that value of Y. And now we can use that to help us solve for X. So if we plug this in for Y, we'll have 45 times 0.95694 and some more decimals plus 1,060 times X equal to 1,000. And now to solve for X, first we need to isolate this term. So we want to multiply 45 by this value of Y and then subtract it from both sides of the equation. If you do that, you'll get 1,060X is equal to 956.93 and some more decimals. And so then you can solve for X by dividing both sides of the equation by 1,060. All right, so I'll do that here. We'll have X is equal to 956.93 and some more decimals divided by 1,060, which will give you that X is equal to 0.90277 and some more decimals. Okay, that is the value of X, or the number of bond A that Flynn needs to buy in order to exactly match his liabilities. All right, and so that's it. We have now found both X and Y, or the number of each of these bonds that Flynn must buy in order to match his liabilities of 1,000 6 months from today and 1 year from today. Now, realistically, it doesn't make sense for somebody to buy 0.95 bonds or 0.902 bonds, right? That doesn't really make sense. You can't do that. But mathematically, these are the right answers to this problem, so we're good. All right, let's move on to the next review problem. Hey there, real quick, before we move on to the next part of this video, if you are currently studying financial mathematics with the intent on taking the exam FM, then I want to give you a gift for watching this video today. I want to give you my free 6-week studying strategy guide for exam FM. Inside the PDF file, I lay out a reasonable studying timeline that you can follow to prepare for the exam FM in just 6 weeks using my own content as well as some other resources online. By all means, it is not the only way to prepare for the exam, but it can certainly help you get started. So if you're struggling to stay organized in your studying of FM topics or want an easy to follow schedule for preparing for your exam, then this guide is for you. And it's absolutely free. Just head on over to jkmathematics.com/studyfm 6 weeks. Once again, that's jkmathematics.com/studyfm 6 weeks. Or you can find the link in the description. Okay, now back to the video. All right, so for our fourth review problem, we have a 30-year bond priced to have an annual effective yield of 10%, has a Macaulay duration of 16.5. After the bond is priced, the yield rate immediately increases by 0.35%. Using a first-order Macaulay approximation, approximate the bond's percent change in price. Okay, so once again, just like with the other review problems, if you want to try this out for yourself first, now is the time to pause the video, and then once you're ready to check your work or compare it to my work, then feel free to play the video again. But now let's get started with this problem here. The first thing I notice is that we are clearly working with price estimation or price approximation, right? We are explicitly told to use a first-order Macaulay approximation to approximate the bond's percent change in price. All right, so for one thing, we are going to have to use this formula, that the price of our bond at a new interest rate, I sub n, is approximately equal to the price at the original interest rate, I naught, multiplied by 1 plus the original interest rate, divided by 1 plus the new interest rate, and that is raised to the power of the Macaulay duration at that original interest rate, I naught. Okay, so we're going to be using this formula, but we're not just going to be approximating the price, we are going to be looking for the approximate percent change in price, and we'll talk about that in a little bit. For now, what I want to do is identify everything that we know, at least with regards to this formula right here. Yes, we know that the bond is a 30-year bond, but we don't really care about that for this problem. We want to know what our original interest rate is, the new interest rate, the original price, and the Macaulay duration at the original interest rate, because that's what we use in this formula. And it looks like our original interest rate or original yield rate is a 10% yield rate. So I naught is equal to 0.10 or 10% as a decimal. And then we're told that after the bond is priced, the yield rate immediately increases by 0.35%. So what that's giving us is a change in the interest rates delta I is equal to 0.35%, which as a decimal is 0.0035. So what that means is that our new interest rate, I sub n, is going to be our original interest rate plus this change in the interest rates. It's going to increase by this amount. So the new interest rate is 0.1035. Okay, now one more thing that we know here is the Macaulay duration. The Macaulay duration at that 10% yield, our original interest rate, our original yield rate is 16.5. So I'll write that down. The Macaulay duration at the original interest rate is equal to 16.5. Okay, so now notice that we don't know what the original price of this bond is, right? We're not told what it is. We have no way of calculating it. It's just simply unknown to us. We don't know what P of I naught is equal to. So we're going to have to find a way around that, which as you'll see is not a huge deal. We still will be able to find the percent change in the price without knowing the original price. All right, but let's say we didn't know that. Let's just put in the information that we have here into this formula. We'll have that the price at the new interest rate, which is 0.1035, is approximately equal to the original price at the interest rate of 0.10 or 10%, multiplied by 1 plus that interest rate of 0.10. So really we have 1.1. So I'll write 1.10, and that will be divided by 1 plus the new interest rate. So we'll have 1.1035. Okay, and then that will be raised to the power of the Macaulay duration at the original interest rate. So we have 16.5 as our power. So we have 16.5. Okay, so we can actually calculate this part. We can take 1.10 divided by 1.1035 and take it to the power of 16.5. If you do that, that quantity will be about 0.9489 and some more decimals. And that's really all we can do in this formula. So let me just write everything else in here. The price at an interest rate of 0.1035 is approximately equal to the price at 10% times this value. Okay, so that's about as far as we can get at this point, but remember what we're actually trying to calculate here. We want to approximate the percent change in price. So let's write out how we would do that. Remember from our formulas at the beginning of this video that the percent change in price, or delta P divided by the original price, is equal to the new price minus the original price divided by the original price. Okay, this is how you calculate the percent change in the price of a bond for these approximations. If we were working with the first order modified approximation, there would be another way to calculate this using a different formula, but for a Macaulay approximation, this is all we have to work with. Okay, you take the change in the prices, or delta P, and divide it by that original price. Now, as I've pointed out many times now, we don't know what that original price is, but watch what happens if we replace the new price with what it's approximately equal to. Okay, I'm going to replace P of I sub n with this expression right here. Remember that this right here, P of 0.10, is the original price of the bond, so that would be the same as these two prices right here. So here's what we have. This will be equal to the original price, P of 0.10, times 0.9489 and some more decimals, minus the original price at 10%, and that will be divided by the original price at 10%. Now notice that every single part of this expression has a factor of that original price. So what we can do is factor out that factor, right? It's just going to cancel out. We can cross this out, and this out. This will just become 1, right? If you factor out the original price from this term, you're going to be left with 1, and then nothing in the denominator. That's just going to disappear. So what this ends up being equal to is 0.9489 and some more decimals minus 1. Okay, and so if you subtract 1, you should get about negative 0.0511. And then if you multiply that by 100, you'll get the percentage for that decimal, and you'll find that the percent change is about negative 5.11%. Okay, that is the percent change in the price of this bond if the yield rate increases by 0.35%. Okay, and by the way, there are more decimals for that. I just decided to round off to 4 decimal places because that makes for a very nice percentage here of negative 5.11%. Okay, and so that's it for this 4th review problem. Let's take a look at the next one. Okay, so for our 5th review problem, we have Grace has a liability of $8,000 due in 5 years. To match this liability, she has payments of X in 3 years and Y in 7 years. If Grace is using a full immunization strategy at an annual effective interest rate of 4%, find X plus Y. Okay, so if you want to try this problem out for yourself, now is the time to pause the video, and then once you're ready to compare your work to my work, you can play the video again. All right, because now I'm going to get started here. In this problem, we are dealing with immunization, specifically full immunization, right? We are told that Grace is using a full immunization strategy at a specific interest rate of 4%, an annual effective interest rate of 4%. Okay, and so that tells us a lot about this scenario. That tells us that the present value of Grace's assets and liabilities are equal. It tells us that their durations are equal, and it tells us that all of her liabilities, which in this case is just 1, will be sandwiched between 2 assets. And when we draw our timeline here, which is what I'm going to do in just a second, you will see that that is the case. You will see that she has 1 liability and there's an asset before and after that liability. So let's do that now. Let's draw a timeline. I think timelines are very helpful for asset liability management problems, whether you're working with exact matching or immunization, doesn't matter. I would always recommend drawing a timeline if you have the time to do so, because it really does help you organize your information and ultimately set up your equations that will help you solve the problem. Okay, so let's draw a timeline here. Mine will look like this. This will be time equals 0. And we're told that Grace has a liability of $8,000 due in 5 years. Okay, so I am going to start with the liability. I do like to put liabilities below the timeline. So the liabilities will go down here. And so this will be time 1, 2, 3, 4, 5. This will be time equals 5, which is where that $8,000 is due. And then to match that liability, Grace has payments of X in 3 years and Y in 7 years. So this is time equals 1, time equals 2, time equals 3, and time equals 4. At time 3, we have an asset of X, and then at time 7, there's an asset of Y, right? She has payments of X in 3 years and Y in 7 years. So this will be time equals 6, and time equals 7, she'll have a payment of Y. Now, I do like to color code them to match the assets, but since they are two different variables that we are going to have to solve for, I do want to give them their own colors. So I'm going to erase these and write them back in like this. We'll have X and Y. All right, that's just going to make it easier to distinguish between the two. We will need to find both of those and then add them together to complete this problem. Okay, but now that's all the information that we've been given besides our annual effective interest rate. We know that I is equal to 0.04. That's 4% as a decimal. So that's the interest rate that she is going to use a full immunization strategy at. Now we just have to create some equations based on the fact that we know Grace is going to be using a full immunization strategy. And as I said earlier, what that means is that, for one thing, the present value of the liability will be equal to the present value of the assets. All right, that's from condition 1 of full immunization. It's also the first condition of Reddington immunization, but we're not really worried about Reddington here since we know we are working with full immunization. Right, the first condition says that the present value of the assets is equal to the present value of the liabilities at this interest rate that we are immunizing at. Okay, and then for the second condition, the durations are going to be equal for the assets and liabilities, and I always prefer to use the Macaulay duration in these types of problems, so that's what I'm going to do here. You could use the modified duration if you wanted to, but it's going to be easier, I think, to use a Macaulay duration. Okay, so from the second condition of full immunization, the Macaulay duration of the assets will be equal to the Macaulay duration of the liabilities at that interest rate of 0.04. Okay, and that third condition is already met. For full immunization, the third condition is that the liabilities are sandwiched between two assets, and as I mentioned earlier, that is now the case. You can see that with the timeline here. Grace has one liability at time 5, and it has an asset before it at time 3, and an asset after it at time 7. So now really, to solve for X and Y, we're going to have these two equations to work with. And so let's start with the present values. Let's set the present value of the assets equal to the present value of the liability. The asset of X is valued at time 3, so we want to value it at time 0 to calculate the present value. So for the assets, we'll have X times V cubed. That will bring that asset back 3 years, and we want to add that to Y brought back 7 years. So we're going to have Y times V to the power of 7. And then that will be equal to the present value of the liability, which is currently at time 5. So we need to bring that $8,000 back 5 years or 5 periods. So we'll have 8,000 times V to the power of 5. Okay, so now we set the present value of the assets equal to the present value of the liability. Now let's work with the durations. Let's calculate the Macaulay duration of the assets. You'll have the present value of the assets, but then multiplied by the time at which they are made, or at which they're going to be received. So we're going to have 3 times X times V cubed plus 7 times Y times V to the power of 7. And that will be divided by the present value, which is X times V cubed plus Y times V to the power of 7. Okay, so X is being received at time 3, so we multiply by time 3. and y is being received at time 7, so we multiply by 7. So that's the time-weighted present value for the Macaulay duration, and then we divide it by the actual present value. So this is our Macaulay duration of the assets, and now we're going to set it equal to the Macaulay duration of the liability, and there's only one of them. We're going to have 8,000, which is at time 5, so the present value of that is 8,000 times v to the power 5, but then we need to multiply it by 5, okay? And then that will be divided by the present value of that liability, which is 8,000 times v to the power 5. Okay, so now, what I always do in immunization problems like this is I like to then simplify the equations we are working with. What I mean by that is notice that we already said that the present values of the assets and liabilities are equal. So when you look at this Macaulay duration equation, right, the MACD for the assets, we're setting it equal to the MACD of the liabilities. The denominators are just the present values, right? We already know that these two things are going to be equal by this first equation. So what we can say is that if these assets and liabilities are going to be fully immunized, this numerator is what needs to be true for the second condition, okay? We're already saying that the denominators are going to be equal because those are the present values of the assets and liabilities. So we really only need to work with the numerators here as our second equation. All right, we're going to have two equations, one from each condition, that are going to allow us to solve this problem. So from the numerators here, we get the following equation. We'll have 3 times x times v cubed plus 7 times y times v to the power of 7 is equal to 5 times 8,000, which is 40,000. So we'll have 40,000 times v to the power of 5. Okay, that's the second equation that we get from that second condition. So now we don't need any of this anymore. We now have two equations that we can work with to solve for x and y, and then add them together to complete the problem. All right, and so now that's our next goal. We want to algebraically solve for x and y in these two equations. And before we try to do anything crazy here, before we try solving for any of these variables, what I want you to notice is that in each term of each part of these two equations, we have a common factor of a present value factor cubed, right? We can reduce all of these terms by a present value factor to the power of 3. So if we divide that out of every single term in both equations, here's what we'll get. We'll have x plus y times v to the fourth power is equal to 8,000 times v to the power of 2. Okay, so we reduced each term by a factor of v to the third power. So now we just have x for the first term. V to the power of 7 becomes v to the power of 4 because we took away 3 of them. And then v to the fifth power becomes v squared for the same reason. And now if we also do the same thing for this equation, we'll have 3 times x plus 7 times y times v to the power of 4, and that will be equal to 40,000 times v squared. All right, once again, we took out v cubed from each term, so 3x times v cubed becomes 3x. This v to the power of 7 becomes v to the power of 4, and this v to the fifth power becomes v squared. Okay, now the reason I did that is because now it makes it really easy for us to solve for x in this equation, and then we can use that to substitute into this one and hopefully solve for y. Okay, because if we subtract y v to the power 4 from both sides of this equation, we will have solved for x. Okay, so let me do that up here. We'll find that x is equal to 8,000 v squared minus y times v to the power of 4. Okay, that's what we find from this equation. Now we can plug what x is equal to in for x in this equation and solve for y. So if I do that, we'll have 3 times 8,000 v squared minus y times v to the power of 4 plus 7 times y times v to the fourth power, and that will be equal to 40,000 v squared. Okay, once again, I just replaced this x with what we found it's equal to. Remember that you need to multiply 3 by both of those values, not just the 8,000 term. You got to multiply by both of them because they are both part of what x is equal to. Now what we want to do is distribute 3 through this quantity and then combine our like terms and hopefully solve for y. Okay, so let's do that next. 3 times 8,000 is 24,000. So we have 24,000 v squared minus 3 times y v to the fourth power. So we have 3 times y v to the fourth power plus 7 times y times v to the fourth power is equal to 40,000 v squared. Now, we have two like terms here that we can combine. We have negative 3y v to the power 4 plus 7y times v to the power 4. We can combine those to be 4 times y v to the fourth power because negative 3 plus 7 is 4. And then at the same time, I'm also going to subtract 24,000 v squared from both sides of the equation. That will nicely subtract from 40,000 v squared. It will leave us with 16,000 v squared. So here's what we're going to get. We'll have 4 times y times v to the power 4 is equal to 16,000 v squared. And now we're almost done. We have almost solved for y. We just need to divide both sides of the equation by 4 times v to the power 4. If you do that, you'll find that y is equal to 16,000 v squared divided by 4 v to the power 4. Now 16,000 divided by 4 is 4,000, and v squared divided by v to the power 4 will be v to the power of negative 2, right? So this would be equal to 4,000 v to the power of negative 2, right? V squared divided by v to the power 4 is v to the power of negative 2 because you subtract the exponents. 2 minus 4 is negative 2. And a present value factor with a negative power is actually the same as an accumulation factor. So really, this is equal to 4,000 times 1 plus the interest rate, which in this case is 0.04. So we'll do 1.04 squared. Okay, so now if we do this calculation, you should find that y is equal to $4,326.40. That's an exact value, by the way. There's no more decimals. And now we can use that to solve for x. If you plug this value of y in right here, multiply it by v to the power 4. Remember that we're using 4% as the interest rate for this present value factor and this one. You'll take 8,000 times v squared minus this value of y times v to the power 4. That will give you x. If you do that, you should find that x is equal to $3,698 and about 22 cents and some more decimals. All right, so once again, I just plugged y in right there to get this value. And now we have both x and y, right? This is x and this is y. So now if you add those two values together, you'll get the final answer to this problem. All right, I'm just going to erase this arrow so I have space to write it. I'm going to do it right here. X plus y is equal to 3,698.22 plus 4,326.4, which will get you $8,024.62. That is the final answer to this problem. For our sixth review problem, we have Benny is expected to receive alimony payments starting today with $200, and then every payment increases by $200 each month thereafter. Assuming the payments last forever, find Benny's modified duration using a monthly effective interest rate of 2%. Okay, so once again, if you want to try this problem out for yourself, if you want to challenge yourself, pause the video now and try it out, see how you do. And then once you're ready to compare your work to my work, play the video again. All right, now I'm going to start working through it here. Notice that in this problem, we are going to be calculating a modified duration. And my preferred way of going about that is to first calculate a Macaulay duration and then just convert it to a modified duration by multiplying by a present value factor. So that's what I'm going to try to do here. And to help me out with that, I'm going to draw a timeline. It will look something like this. This will be time equals 0. And then we know that Benny is expected to receive alimony payments starting today with $200, and then every payment increases by $200 each month thereafter. Okay, so at time 0, he is going to get a payment of $200. So I'll put 200 right there. And then it looks like we're working in terms of months. So time equals 1 would be 1 month in the future. Time equals 2 would be 2 months in the future. Time equals 3 is 3 months. Time equals 4 is 4 months. Time equals 5 is 5 months, and so on. This is going to go on forever because we're told to assume that the payments last forever. Okay, so this is going to be a perpetuity of some kind that we are calculating the modified duration of. All right, now every payment after the original increases by 200. So we'll have 400 at time 1, 600 at time 2, 800 at time 3, 1,000 at time 4, and then 1,200 at time 5. And of course, that would continue on forever, but I'm going to stop there. It doesn't make sense for us to draw out any more than that. Okay, now remember, I want to calculate a Macaulay duration first, so let's set that up. The Macaulay duration is equal to a time-weighted present value divided by the present value. And so we have a $200 payment at time 0. So that's already valued at time 0. We don't need to multiply it by any present value factors, but we're going to be multiplying it by the time at which it is received, which is time 0. So we start with 0 times 200, which is a little bit weird, but that's okay. Then we'll have plus 400 at time 1. So that needs to be brought back 1 period. You'll have 1 times 400 times V. And then 600 needs to be brought back 2 years, but then you also want to multiply by 2. So we have plus 2 times 600 V squared. And then if you were to do the next one, it would be 3 times 800 V cubed. And that would go on forever, right? That will never end. And the same will be true in the denominator. We're just going to have the present value of these payments this time. We're not going to be multiplying them by the time at which they are made or when they're going to be received. So we have 200 plus 400V plus 600 V squared plus 800 V cubed, and so on. And now this is where things get a little bit tricky. Because so far in this video, you might have noticed that when we are calculating Macaulay durations, in this way, that we were working with a finite number of payments. We were not working with an infinite number of payments like we are here. So this makes things a little bit tricky. We have to find a way to represent these streams of payments with a closed formula that we can actually calculate the value of, but that might actually prove to be difficult when it comes to the numerator. The denominator is not so bad because this is just an arithmetic increasing perpetuity. You start with a payment of 200 and then every payment after increases by 200. This is just an arithmetic increasing perpetuity due since the first payment starts today or at time 0. So we could easily represent that with the formula for calculating the present value of an arithmetic increasing perpetuity due. But what about the numerator? That's where things are going to get tricky. This term is just 0 because anything times 0 is 0, but then we have 400 times V, and then 2 times 600, which is 1200 V squared, and then 2400 times V cubed, right? If you were to simplify, this would be 400 V, and then you'd have 1200 V squared, and then 2400 V cubed. And then if you were to look at another one, you would have 4 times 1000, so you'd have 4000 V to the power of 4. Look at those payment amounts. We don't really have a clear pattern there, right? We're at 400, then 1200, then 2400, and then 4000. The payments are not increasing by a set amount. We increase by 800, then 1200, and then 1600. That's not a type of annuity or perpetuity that we have a closed formula for. We don't know how to easily calculate that present value. So it looks like this method of calculating the modified duration is not going to work here. It's going to be too difficult for us to do. All right, if the payments didn't go on forever, we could work with this, it'd be fine. But since they do go on forever, it's impossible for us to take all of those payments into account without coming up with some type of closed formula like we can in the denominator. We can't do that in the top, so we kind of get stuck here. This method isn't going to work. We're not going to be able to calculate a Macaulay duration and then convert it to a modified duration. We have to find another way. So this is a bust. I'm going to erase this. We have to start from scratch. We got to figure out another way to calculate this modified duration. And so here's what I'm thinking we try to do. Remember that a modified duration can also be calculated by taking the negative first derivative of a present value function and dividing it by the original present value function. What we should try to do here is come up with a present value function to represent this stream of payments, okay? And we can do that. If you remember when we were talking about the Macaulay duration calculation, the denominator was not the part that we were having trouble with. It was the numerator. The denominator of a Macaulay duration is just the present value of the set of cash flows, which we have identified to be an arithmetic increasing perpetuity due. So we should be able to create a present value function, right? The present value function P of I would be equal to the formula for calculating the present value of this arithmetic increasing perpetuity due. The formula for an arithmetic increasing perpetuity immediate looks like this. That's what we have to start with, and then we'll make it a due formula. We'll have the initial payment of 200 divided by I plus the increment, or the amount that every payment increases by, which is also 200 divided by I squared, right? Remember, this is the formula for calculating the present value of an arithmetic increasing perpetuity immediate. But now we are working with a perpetuity due. The first payment is at time 0, so we need to multiply by a factor of 1 plus I, an accumulation factor to the first power. Okay, that is how we calculate the present value of an arithmetic increasing perpetuity due. All right, I know I keep saying that. That's probably like the 5th time I've said that now, but I just want to make sure that it's clear what we're working with here. And if you're not familiar with this formula or you forgot it, make sure to go back to Unit 2, where we talk about how we value different types of annuities and perpetuities. Okay, but now we have a price function that we can work with. So if we want to calculate the modified duration at an interest rate of 2%, which, by the way, let me write that down. We have a monthly effective interest rate, which would be J sub 12. That's equal to 2%, or 0.02. That's the interest rate we want to evaluate our price function and its derivative at in order to calculate the modified duration. But in order to do that, we do need to find that first derivative, so we will have to take the derivative of the price function we set up, which at the moment would require the product rule for derivatives. And if you remember how to do the product rule for derivatives, feel free to do that. But I'm going to try to simplify this function a little bit before I take its derivative. That way I don't have to use the product rule. What I'm going to do is multiply 1 plus I by each of these terms. And I'm also going to pull 200 out of these two terms for now. So this is what we'll get. This will be equal to 200 times 1 plus I divided by I plus 1 plus I divided by I squared. All right, so I pulled 200 out of those two terms and then multiplied 1 plus I in, so we have 1 plus I in the numerator of each term. Now, what I want to do is simplify this by breaking up these fractions. We'll have 1 divided by I plus I divided by I, and then we'll be adding that to 1 divided by I squared plus I divided by I squared. Okay, so let me continue that up here. This will be equal to 200 times 1 divided by I plus I divided by I plus 1 divided by I squared plus I divided by I squared. Okay, so I just split those two fractions. Now we have 4 terms, and this I divided by I squared, one I will cancel out in the numerator and denominator. This just becomes 1 divided by I, all right? And then I divided by I is 1. So this is equal to 200 times 1 divided by I plus 1 divided by I squared plus 1 divided by I. And now we have 2 like terms, 1 divided by I and 1 divided by I. We can add those together to get 2 divided by I. So here's what we have. This will be equal to 200 times 1 plus 2 divided by I plus 1 divided by I squared. Okay, so we have this 1 right here. Then 1 divided by I plus 1 divided by I is 2 divided by I, and then we're adding 1 divided by I squared. Okay, now one more thing I want to do to make it easier for us to take the derivative here is move these i's in the denominator to the numerator of their respective terms by making their exponents negative. So we'll have that this is equal to 200 times 1 plus 2 times I to the power of negative 1 plus I to the power of negative 2. Okay, so I moved this I to the numerator, so now we have 2 times I to the power of negative 1, and then this I squared to the numerator just makes this term I to the power of negative 2. Okay, and then one more thing I'll do here, you don't have to do this, but I'm going to distribute this 200 back through this quantity. All right, so I'm just going to write that below our original present value function. This will be equal to 200 plus 400 times I to the power of negative 1 plus 200 times I to the power of negative 2. Okay? So now we have the present value function that we want to work with here. It's nice and simple. We can very easily take its derivative, which would be p prime of I, and we need that in order to calculate the modified duration. So let's take the derivative here. P prime of I will be equal to the derivative of 200, which is 0. 200 is a constant. The derivative of all constants is 0, so I'm not going to write anything for that. But then for these two terms, We are taking a derivative with respect to I, remember that. So for both terms, we will need to use the power rule for derivatives. We'll multiply the -1 down, so we'll get -400 times I, and then we need to subtract 1 from the exponent, so our exponent will be -2. And then we'll take the derivative of this term. We need to multiply -2 down, so -2 times 200 is -400. So we have minus 400 times I to the power of -3, right? We subtract 1 from that exponent, so -2 becomes -3. So now we have both the present value function and its derivative that we can use for this modified duration at a monthly effective interest rate of 2%. And I should clarify here, I was a little sloppy with my notation. I am assuming that these I's are a monthly effective interest rate, okay? All of these periods represent a month. So these payments are being made monthly. So when you set up this formula for the present value of an arithmetic increasing perpetuity due, you need to make sure that all of those I's, or those interest rates that you use in the formula, match the payment cycle. So if the payments are being made monthly, those interest rates should also be monthly, okay? I didn't want to write J sub 12 a million times when we were finding this present value function or when we were simplifying it. So I just wrote I, but do note that this was set up with a monthly effective interest rate in mind, okay? But now we're actually going to plug in 0.02 for each of those I's to calculate this modified duration. All right, so here's what we're going to have. The modified duration at an interest rate of 0.02, that's the monthly effective interest rate, for Benny's alimony payments, the modified duration will be equal to the negative derivative of the present value function evaluated at 0.02 divided by the original price function evaluated at 0.02. And so here's what that will look like. I'll write it like this. We'll have negative 400 0.02 to the power of -2 minus 400 times 0.02 to the power of -3. That takes care of the first derivative. And then in the denominator, we have the original present value function. So 200 plus 400 times 0.02 to the power of -1 plus 200 times 0.02 to the power of -2. Okay, that is the full calculation for the modified duration of Benny's alimony payments that go on forever. Or in other words, his arithmetic increasing perpetuity due. So if you plug this into your calculator, here's what you'll get. The modified duration for a 2% monthly effective interest rate is 98.0392 and some more decimals, but I'll round it off there. That is the final answer to this problem, okay? That is the modified duration. All right, so from this problem, we learned something pretty important, and that's this. When you go to calculate a modified duration, and you try to do it the easiest way of calculating a Macaulay duration and then converting it, if you get stuck on that, if the Macaulay duration calculation is just too hard, there's no way for you to calculate it because of the way the payments are structured, what you can do, if it makes sense, is create a present value function that represents how you would calculate the present value of the payments or the cash flows that you're working with, take its derivative, and then use this formula instead. In fact, you could also do this for a Macaulay duration. If we wanted the Macaulay duration instead of the modified, you could just take this value that we just calculated and multiply it by 1 plus the interest rate, and that would be the Macaulay duration, okay? So this is always an option. It doesn't happen often. This is not something that you will have to do a lot, but it is something that you want to keep in mind. Usually I say you only want to use this formula when you're given a present value function, but in this case, we had to make that present value function ourselves because calculating the duration the other way just wasn't feasible. It just wasn't going to happen. All right, but that's it for my 6th review problem for Unit 5 on cash flow duration and immunization, and it's also the last review problem for this video. However, I do have 4 more review problems available exclusively on my membership site, JKMath Plus. I have review problems 7, 8, 9, and 10 available there for members. And so if you're looking for some more practice on these topics, feel free to look into becoming a member. There's a lot more on the membership site than just those 4 review problems. There's also extra review problems for the other units in financial mathematics, as well as just some other bonus videos for financial mathematics. and there's a whole lot more on there as well. You can find out all the details by heading on over to my website at jkmathematics.com/plus. Okay, so if that sounds interesting to you, feel free to check that out. But with that, that is all I had for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, that is all I had for now. So I will see you next time.